right, so we'll pick this back up again and talk about suspended load. Again, I apologize for not breaking that up into two when I put the lectures together. I didn't realize it was going to take quite as long as it would. So we're going to now talk about suspended load and how particles move in suspension and how we describe the turbulent and fluid dynamic characteristics that result in the suspension of particles. And ultimately, we're going to derive a formula for the profile of suspended sediment concentrations in a flow. It's something that comes up a lot in conversations about rivers and about suspended sediment transport. And so I think it's worth talking about here in the context of how it results in sedimentation. Okay, so here's a picture, for example, of the Mississippi River at relatively high discharge. I believe this was from 2019, although I'm not 100% sure that I remember when I pulled this satellite photo down. But you can see the amount of fine sediment that's being transported in suspension in this river is quite high, and so it's suspended sediment transport is a relatively important component, if not the most important component in much of the world's, especially the world's large rivers. So in the Mississippi River here, more than 95 to 98% of the sediment that gets moved down this river get moved in suspended load rather than bed load, and that varies depending on the river that you're in, the time of year, the flood stage, right, and the grain size. So different rivers may be bed load dominated versus suspended load dominated, and this happens to be a suspended load dominated river here. Okay. Just again to reiterate, as I mentioned before, the suspended load is the component that moves here up in the upper portions of the flow. It's the particles that have essentially detached themselves from the bed and have moved in such a way that they've gone up into the, they've ejected from the bed load layer and are now sort of moving through the flow with the velocity of the fluid itself. So they are moving as turbulent eddies move them up and down and downstream, and they're free to travel, many thousands of times their length, their diameter, right, downstream. So you can see what this looks like in a flume experiment here. Maybe. Oh, I guess that was not a video here. We didn't embed the video. Here's an experiment from a flume in Wageningen in the Netherlands. I believe this was in Wageningen. But it is in the Netherlands. A colleague of mine took these, and you can see these bursts of sand here that are in the water column, and those are the suspended load. That's suspended sand, so that would be bed material load, suspended bed material load, right? Up high in the flow, well detached from the bed itself. And these would be moving downstream. I can find some videos of this for you. I thought I had embedded a video of this, but I guess I did not. And you can kind of see vaguely in this image, you see sort of a little bit of a lighter band above the bed there. That's the bed load layer. So you can see there's a bunch of particles in saltation, and then a bunch of sediment that's being picked up into the flow primarily by turbulent eddies, what we would call bursts and sweeps, which are turbulent eddies that either go downward, sort of downward and downstream facing into the flow, or upward and downstream facing, which have the effect of ejecting a bunch of sediment all at once up into the suspended load layer. Okay, and so you can think about suspended load concentration, how much sediment is in the water column, as a ratio of volume of sediment to volume of water, or mass of sediment to volume of water, or something like that. It gets reported in all of those different ways as a function of how much turbulence is available to sweep sediment off the bed and eject it up into the flow, right? So that's one of the main drivers, right? And we can kind of talk about that here. So if you're in a flow like this, here's a cartoon version of a river in this case, and you have the bed down here that's composed of loose sediment, sediment that's available to be moved by the fluid, right? So it's grains of sand, it's not bedrock. And then you have a bed load layer. These are the particles that are moving as saltating, rolling, and sliding grains, or a bed load sheet if it's that type of flow. And so we would define the top of the bed load layer at the point at which a significant portion, the height at which a significant portion of the particle, the saltating particles would reach to, right? And that's the reference layer that we sort of set as the lower boundary of our suspended sediment profile. And up here in the flow is generally going to be moving in a turbulent fashion, right? So there's big turbulent eddies that are moving around. And it's the turbulent eddies as they impinge on the bedload layer and on the bed itself that can eject particles upward. And so it's this diffusion of sediment from this high concentration bedload layer to the low concentration upper region by turbulence that moves sediment upwards, right? It's sort of like it's similar in concept to other diffusion-related problems where it's the gradient, right? The difference between the concentration at the low point where it's high concentration and the concentration at the high point where it's low concentration in the flow, right, is part of what sets the gradient. It's part of what sets the diffusivity between the two that brings sediment upwards, right? But in this case, even though turbulence may be constant, you don't end up like you would if you put a drop of water, of food coloring into a cup of water and you get diffusion outwards from there, which is based on the concentration, right? It's a similar problem. That's a non-turbulent version. This is a turbulent version. But in this case, turbulence is going to be constant. And so you would think what would happen is once you reach an equilibrium state, all of the particles would move upwards and you would smear it out and it would be a uniform concentration from the bottom to the top, right? That would be what you might predict if you're thinking about diffusion like the food coloring in a cup of water chemistry version. But that's not true because there's a resisting force in this case. So the driver of suspension into the water column is that turbulent diffusion, but the resistor is the fact that gravity is always pulling those particles downwards. And so because of that, you have a settling of those particles or a resistance to that upward diffusion, up to that turbulent motion upwards, that results in the particles wanting to stay closer to the bed. And so it's those two things in competition that determine what concentration of sediment you have at what level of the flow, okay? And so we can kind of talk about this and sort of heuristically derive what that profile might look like in a suspending fluid, if you will. So in this case, we have our river here. This is the top of the river. This is the bed here. So we have a reference frame at the top of the bed, which in this case we'll call Z0, and we have the height of the bedload layer here, which is often denoted by this Greek letter, or by del here, del B, and you'll hear me refer to that as the height of the bedload layer, or del B. And then you have a velocity profile, right? And so when you're deriving the velocity profile, you end up with a logarithmic shape, okay? And we didn't really cover this in class in much detail, and I apologize that somebody has decided to start mowing their lawn or something. This always seems to happen at 4 p.m. on Tuesdays here. But hopefully it's not too distracting. In this case, as you go further away from the bed, you sort of even out your velocity profile here, right? So you have high friction at Z0, the height of the roughness on the bed, right? So that's sort of where the velocity approaches zero here because of the friction at the bed, right? And then the velocity profile is quite steep here in the sense that the velocity is increasing very quickly, right, as you go further away from the bed. And that slows and slows and slows as you get further away from the effects of the friction of the bed until you reach this sort of almost vertical velocity profile where the velocity here is nearly the same as here, is nearly the same as here, is nearly the same as here. Does that make sense to everybody? So this is turbulent flow up here, right? And the turbulent eddies are maybe smaller down here than they could be here and so forth, and they're larger up here. And it's this turbulent flow within this velocity profile that sets the ability of the flow to take particles from the bedload layer at del B and move them upwards, okay? And then that is balancing, that is being balanced by the downward settling of the particles in the flow, right? So we have now the particles. So this is what sets the upward diffusion component, right? And then we have the downward settling of the particle that has to work in an equilibrium sense to balance the drag forces that are pushing that particle upwards, right? So it's the drag of the fluid turbulence moving around a particle that pulls it up. And then if the particle's not moving, then it's in balance with the downward settling velocity, right? And that downward settling it's an acceleration due to gravity, right? In a still water system, right, you can think about dropping a cobble versus dropping a grain of sand versus dropping a grain of silt into a graduated cylinder, right? The cobble is going to move much faster. The sand will move slower. The silt will move even slower, right? Particle settling velocity is a function of the grain size, the density, right? So if you put a piece of, a gravel-sized lead sinker from your fishing tackle box in there, it's going to settle faster than a same-sized piece of quartz sand, right? Because of the density. If it's super angular versus round, the shape will matter because that changes the turbulent characteristics around the particle and the drag that the particle experiences or exerts on the flow, right? And the concentration actually matters too. So in really high concentration flows, the particle settling velocity can be slowed down by the fact that other particles are interacting with each other or interacting with the wakes from other particles as they settle. We won't deal with too many situations like that until we get to turbidity currents later on in the semester. But also fluid properties, right? So the density and the viscosity will determine how fast a particle settles as well, okay? And so all of those terms go into a formulation that we can use to then calculate what the settling velocity is. And you can find calculations for this, or you can measure it. It's quite complicated because of all of those different parameters that affect it. And so there's several different ways that you can formulate it. These two references are there if you ever need to calculate it for a particle. But know that like a 300 micron grain of sand, which is a normal river grain of sand, is somewhere around about, is going to settle at somewhere around about a couple to 3 centimeters a second. Okay. And so it's that downward settling of the particle that then has to balance that upward turbulent diffusivity to result in a concentration profile, right? So you're moving particles upwards, but they're resisting that and they're trying to pull back downwards. And so every time a turbulent eddy lifts a particle up, it gets settled back down a little bit when that eddy, slows down, or it resists just a little bit. And so you ultimately end up with a profile that looks like this. It's you might recognize that as sort of an exponential function, a decay function, right? And there's a mathematical formulation that gets used to describe this, and maybe at either office hours or at next week's discussion, I can actually derive this equation for you if people are interested, because we can derive it from first principles from basic mathematics. But it looks like this. This is called the Rouse profile, and it is that the concentration of sediment at some elevation above the bed divided by the concentration at the reference height ZA, that height is often taken to be the height of the bedload layer, del B, if you remember that. Um, so everything is relative to the height, to the concentration that from which you are grabbing sediment upwards from, right? So you can set that anywhere. If you know the concentration here, then you can start to calculate it for any point above there. Does that make sense? Right? And it's a function of your height relative to the reference height to the power of this term minus p. And p is called the Rouse number. And it takes the following form or definition. And the minus is there is because it's sort of an opposite of your intuition of a driving versus resisting relationship, wherein this is the resisting term here, the settling velocity Ws, right? So this is what's resisting particles moving upwards into suspension. That's the downward directed force, if you will. And then the denominator term here is the driving force. This is the turbulent diffusivity term upwards, okay? This is what is causing sediment to want to move upwards into the flow and create suspension in the flow. And it's a function of this term called alpha, which we just take as 1 in most fluid systems. It can vary in high concentration flows, but we won't go into that. And then this kappa, which is called von Karman's constant, and that's just 0.41. It's a constant also in low concentration flows. Times that term that I introduced before, U star here, and that's the fluid shear velocity. It's the term that represents the turbulence in the flow, okay? And so you can see that as settling velocity is large and shear velocity is small, this number is going to be big, and so your concentration, the exponent is going to be a large negative exponent, which means that your concentration is going to fall off very quickly as you get further away from the bed, right? So you're going to have a very steep profile, which means very low concentrations high in the flow, and and the higher concentrations are going to be very much focused towards the low end of the flow. If you have a high shear velocity and a low settling velocity, high shear velocity U star and a low settling velocity Ws, then that's going to be a very small number, right? And that's going to result in a steepening and flattening and higher concentration further away, if that makes sense. So here are some values of this for, or here's some example profiles of a Rouse profile for different values of Rouse numbers, and these are the Rouse numbers here listed in for each of these curves. And so 1.93 you can see is a relatively high Rouse number and relatively low suspension concentrations, right? Where you see that the majority of the suspended sediment is near the bed, right? And then as you get higher up in the flow, there's very little suspended sediment reaching those upper regions of the flow, and it actually approximates 0 as you get further up here. And as you lower that Rouse number, you increase the suspension and you increase the uniformity, if you will, of the concentration profile from the bottom to the top, right? It becomes more uniform as you go upwards. And typically a flow is considered sort of fully suspended load dominated at Rouse numbers of around 0.8 to 1 and lower, right? And then as you get into Rouse numbers of 0.8 or so to about 2.5, you're considered to be in mixed load, where you have a lot of suspended load and a lot of bed load both. And then at Rouse numbers of about 2.5 and greater, there's very little suspended load. It's all bed load dominated. This is sort of the general notion, okay? And I mention all of this to say that suspended load matters quite a bit in most large river systems, and is the dominant process by which sediment is delivered from the continents to the oceans, right? And you can do an accounting of this based on using equations like the Rouse profile to estimate the suspended load discharges of some of these rivers, right? And you can ultimately come up with these types of graphs here where you can see that most of these rivers, the total load that's being delivered is dominated by suspended load. So here's the Amazon, for example, and almost all of the total load of the Amazon and certainly almost all of the total load of the Yellow River and the Yangtze River and the Ganges Brahmaputra River are dominated by suspended load. Okay, the Yukon maybe has more bed load, but is still a suspended load dominated river. Here's the Mississippi River here, and so the annual amount of suspended sediment that gets delivered to the oceans is enormous, and so that's why it's important. It's both important for fluvial systems when we're talking about fluvial sedimentology and stratigraphy, but it's also important when we're starting to talk about coastal, deltaic, marine, offshore, etc. Okay. Sorry. So that kind of concludes the discussion of sediment load for this week. We'll talk next about sedimentary structures, and then we'll go from there. All right.